Okay, hello everyone. Today's speaker is Igor Sikora. So he's going to tell us about equivariant contextuality.
Yes, thank you, and thank you for the invitation to be kind of back in Bilkent, even though remotely. So firstly, I need to do a small disclaimer. There might be a situation that I will be needing a 3 minutes break because my little one is sleeping in the other room, the room where I'm usually working. So I might need to move my laptop and all of the other stuff. So I just wanted to say this beforehand. Okay, but this might not happen. We'll see. Okay, anyway, so let me start with a kind of motivating example. I should firstly say that equivariant contextuality is, of course, joint work with Cihan. And this will appear on arXiv soon. So let me start with a, well, maybe not so motivating example, but an example of an idea we want to capture. So let us consider here the following two spaces, Simplicial sets. So we'll take X to be just a sphere and Y, X will be a torus and Y will be just a one-dimensional sphere. And we want to consider simplicial distributions from X to dry. So I will be recalling the basic definitions a little bit later, but since I think that simplicial distributions were already discussed a couple of times on this seminar, I assume that it will be more or less clear what I'm talking about. So the question is, how do we describe them? So first, we would like to take a look on all simplicial distributions from a torus to distributions on a sphere. So what we do is firstly, we embed the circle in the nerve of Z2 by sigma 0, 1 goes to 1. Here, sigma 0, 1 is non-trivial, non-degenerate. One simplex of S1. And then, well, we know that distributions from a two-dimensional simplex to dr on the nerve of Z2 are determined by a tuple that's P00, P01, P11, P10, and P11, such that the sum of PAB is equal to 1. So by the embedding we gave a moment ago, we get that distributions from a two-dimensional simplex to dr on S1 are specified by such tuples with P11 equal to 0. Okay, so having this, we can, in general, describe the simplicial distributions simplicial distributions on x and y as a set of pairs T1 and T2 belonging to 0, 1 squared, such that T1 plus T2 is less or equal than 1. And here is a small picture. So these two edges are the same, so we'll have T1 here. These two edges are the same, so we'll have T2 here. And here we'll have, this has to be 0 by the discussion on the embedding of the circle in the nerve. And here we'll have T1 plus T2 bar here as well. And this is just an abbreviation for 1 minus T1 plus T2. Okay, so this is the description of simplicial distributions on a torus. But here, what is happening is that we can endow, or we actually have an action of a group C2 on the torus, and the action is given just by swapping the edges. And we want to understand what is happening if we require the distributions to be invariant under this action.
Oh, okay. I have a question. So your way of placing these T's is slightly different than the convention of, putting these numbers on the triangle. I think you're labeling the edges and you're not labeling the inside of the triangle with these 4 numbers, right? It's something different.
Okay, sorry. So I'm not really used to this convention. Okay, I see. Is this what you mean?
Yeah.
So I was following the usual convention, but okay, maybe incorrectly placing the numbers. So the question is, what is happening if we require the distributions to be invariant under the action? And in this example, it is quite easy to see what will happen. Well, in this case, we'll get that T1 is equal to T2. So then we can describe these invariant distributions. We'll have kind of one point of freedom, and we can write it as 0 to half. And here, one of the examples which we have is if we require T1 to be 0, then what we get is the deterministic distribution. Delta 0, 0. And this will occur to be the only equivariant deterministic distribution. So this is the idea which we would like to capture, the distributions which are equivariant, so invariant under the group action, and well, how we can capture them, what they tell us about contextuality, and yes, these are the questions. So let me now recall some basic definitions. Oh, sorry. So we start with R, which is a zero-sum free ring. semi-ring, which means that if A plus B is equal to 0, then A is equal to B is equal to 0. In other words, no element of R have additive inverse. And then we have the monad dr on sets. So what does it do on objects of sets? Well, dru is a set of finitely supported functions u to r, such that sum of u over whole u p of u is equal to 1. And drf, so what does it do on morphisms? For f going from u to v is defined by this formula. So this is the formula which Aziz used to throw here and there quite often. In particular, I think this is something already known. And using this monad, for a simplicial set X, which we think about as a functor from the simplex category to sets, we define a simplicial set drx simply as a composition of delta op x to sets and then dr in sets. And so what I'm here referring to is work of Cihan, Selman, and Aziz on simplicial quantum contextuality. And the basic definition from this paper is the following one, that let x, y be simplicial sets, then simplicial distribution on x, y is a simplicial map x to dry. And a deterministic distribution is a distribution of the form so here we have a simplicial map, and here we have delta map. So what is delta doing? Well, it is sending a simplex of y, the distribution which is picked at that simplex. So it takes value 1 at this simplex and 0 everywhere else. And we have this comparison map theta. going from dr on deterministic distributions on xy. So this is usually referred to in a paper as classical distributions. And it goes to simplicial distributions on xy. And what does this map do? Well, so we start from a probabilistic mixture of deterministic distributions, and we send it to a distribution D, the simplicial distribution theta D, going from x to dr of y, such that value of theta D on a simplex sigma, well, it has to be distribution on y. So what does it do? Yes, I'm having a mistake in my notation. This is capital theta. And here we have small theta. And what this map does, it sends a simplex small theta to the sum of dr. So these are, for people not familiar with this, these drs over here, such that the map R, the value of map R on the simplex sigma is equal to small theta. So this is how this comparison map is defined. And a distribution is called non-contextual if it is in the image of theta. Capital theta. Otherwise, it's called contextual. Yes, so I think most of the people here already know this stuff. Of course, the idea behind this notion of simplicial contextuality comes from physics. But here we treat it kind of as a simply topological idea. Now, so this is what was done in simplicial quantum contextuality. And now let's add here a group action. So once again, we start with a set, but this time we will take U to be a G set for some finite group G. Then we can equip DRU, so these distributions on U, with a G action given by G acting on the function P on some element U is just equal to P of G inverse U. And here, this is a usual conjugation action where we assume that the action on R is trivial. Okay, and this construction extends to G simplicial sets. Okay, so what is a set? What is a simplicial distribution? Simplicial distribution is a map from X to dry, and here, if we take Y to be a G simplicial set, then we have just constructed an action of G also on dry. So then we come to a quite intuitive definition that if X and Y are G simplicial sets, then a G equivariant simplicial distribution on XY is a simplicial G map X to dry. And a G equivariant deterministic distribution is the simplicial distribution of the form. So once again, we start with a map from X to Y, and then we have this delta distribution, dry, but this time we take a G equivariant map here. So this is also usual idea how we define equivariant stuff. We take a non-equivariant definition and we put words G equivariant everywhere where we can. And we will see what we can get out of this. And then we have also, once again, we have comparison map. This time, this comparison map doesn't change, so it is the same. But we can restrict its domain to G equivalent deterministic distributions, to probabilistic mixtures of G equivalent deterministic distributions. This map goes to G equivalent distributions. And we say that a G equivalent simplicial distribution P is G equivalently non-contextual if it lies in the image of theta G. Otherwise, we call it G-equivalently contextual. Now, here the important thing is that we only consider here the domain of this map only G-equivariant deterministic distributions, and by this we get that far less distributions are G-equivalently contextual. Because is this right? Just a moment. Yes. So what I want to say is, it's easier to be classically, well, non-equivalently contextual than G-equivalently contextual, because we have no, it's other way around, right? So if something is G-equivalently contextual, then it is contextual, but if it's contextual, that it doesn't have to be G-equivalently contextual. So it's this way around. Because here in the domain, we have usually less points than in just non-equivalent contextuality definition. Yes.
Okay, so I mean, yeah, so from the non-contextuality point of view, it's G-equivalent and non-contextual, then it's non-contextual is the correct direction, because you can already write it as a probabilistic mixture of G-equivalent functions, right? So that would imply ordinary non-contextual. So you have to negate this to get the contextual.
Yes.
Yeah.
So what I said wasn't correct, but it's easier to be non-contextual than be
I'm not sure.
not contextual.
Yeah, maybe what you said was correct, but I mean, from non-contextuality, it's easier to see it.
Yeah. Okay. So what we would like to do is we would like to connect this idea with the Borel construction. So here, let me just, for completeness, give the definition of EG. So EG is a simplicial set given by EGN is equal to GN plus 1 and DI of G0, G1, blah, 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 up to Gn is equal to G0, Gi times Gi plus 1, Gn, for 0 less or equal than I smaller than n, and G0 up to Gn minus 1 for I equal to n. And the degeneracies are given by putting 1 in the ith place. Okay. So this simplicial set is free G set, and we have the universal principal G bundle. G, EG goes to the nerf G. Now, what is a Borel construction? If we start with a G simplicial set, then the Borel construction on X will denote it by X double slash G is defined by x g n is equal to e g n times over g with xn. So is it clear for everybody what this thing over here means? Okay, so I assume that it's clear. Okay, and usually what we have is that if we have a simplicial G map, then there is the following commutative diagram. EG times X goes to EG times Y. Here we have identity times F. Here we have projections. So this goes to X, to the Borel construction on X. And this goes to Borel construction on Y. So here we'll have a map, quotient map between Borel constructions. We use different notation for this, sorry. And really what this diagram is telling us is that if we have a G map between simplicial sets, then it gives us a map between Borel constructions. Okay, and the one of the important and very easy Borel construction which we are going to use is the following one. So if G acts trivially on Y, then the Borel construction is just a product EG times Y, and G times Y, sorry. And in this case, if we have, once again, simplicial G map between X and Y, we will define the following map. F twiddle G goes from the Borel construction on X to Borel construction on Y, but this is equal to NG times Y. And here we take the projection on the second factor on Y. And so F twiddle G is the composition of these two maps. Yes, and in particular, what does it give us is that if we have if Y has trivial G action, then if we start with a simplicial G equivalent simplicial distribution from X to dRy, we get this P twiddle, which goes from the Borel construction on X to dRy. Now, yes, now we would like to connect this notion of G equivariant contextuality to the Borel construction, and this goes as follows. So we have this comparison map. So this is this equivariant comparison map. But we can yes. Okay. Here we have the usual comparison map. So the sorry. On the Borel construction. Yes, so we have this diagram, and from this diagram, we get the following thing, that G equivariant simplicial distribution P is G equivalently contextual if and only if P twiddle G is contextual. Okay, and so how we get it from this diagram, we actually have vertical maps in both directions. So yes, just a moment. Okay, I want this, yeah. Yes, here what we do is we send the deterministic distributions to deterministic distributions, and this defines the whole map. And here what we do is we take P to P twiddle G. And so these are the downward arrows. The upward arrows are simply obtained by restriction along the inclusion X to the Borel construction. Now, if we have these really two diagrams, it's easy to see that this proposition is true, because let's see it from a point of view of non-contextuality. So if P is non-contextual, it is hit by something over here, right? Yes, but then by the dashed arrow, it goes to something over here, something over here. So there is also distribution over here, which hits the image under the dashed arrow. And similarly, we can get that if we are G equivalently non-contextual, that means that there is something which hits our distribution. But then by the commutativity of diagram, we once again get that P twiddle G is also non-contextual. Okay, and our goal here is to connect, or our further goal is to connect this discussion to group extensions. But here I'm putting quotation marks, as these are not group extensions, but this will be partial group extensions, and we want to use similar ideas which are in group cohomology theory. But to this end, we need one more definition. What does it mean to be relative to Y? what is a distribution relative to y. So if we start with y with I being a G-equivariant inclusion, then a G-equivariant distribution on xy relative to y is a G-equivariant distribution P from x to dry such that the following diagram commute. So we have that y, here we have our inclusion goes to x, here we have dry, and here we have the delta map. And here we have the distribution P. And of course, this is not really specific to G-equivalent distributions. If we take G to be a trivial group, we then obtain what does it mean to just be a distribution relative to Y. And an easy technical result is if x to dy is well, maybe I will just write G distribution rather than equivariant. The G distribution relative to Y, then the distribution, so here we start with P, then P twiddle G going from X double slash G, so the Borel construction to the RY is also relative to Y. Okay, and let me pause a moment here, to discuss the second motivation for this whole project. So now I will be referring to the work of Cihan, Robert Raussendorf, and Stephen Bartlett, I think. So the topological parity paper. What are the names? Cihan, Sam Roberts, Stephen Bartlett, and Robert Raussendorf. So I'm referring to topological proofs of contextuality in quantum mechanics. Sorry, my tablet decided to disconnect. Okay, can you see motivation 2 and the whiteboard again? Okay, very good. So usually how we call this paper is top par for topological parity proofs. So how the contextuality was detected in this paper? So firstly, we start with a set of observables all such that all O in O are distortion. So in particular, their eigenvalues are d roots of unity. Then we identify among these set of observables an indexing set E, and a subset of O such that all observables in O can be recovered from these observables indexed over E up to this root of unity. So really what we can see here is whatever it means at this point is that we have kind of an extension of ZD going to O, and then we kind of quotient this by ZD, so we go to E. I'm not making any precise sense of this statement, but rather I'm giving this as an idea of thinking about it as an extension. Now, if two operators TA and TB commute, then we have the relation that TA plus B is equal to TA times TB up to some constant, up to some function beta on AB, which becomes a two cochain. Yes, maybe let's write it like this, E squared to ZD. But really, we think about beta as a cochain, two cochain on E. And this two cochain occurs to be a cocycle, and if the cohomology class of beta is non-zero, then O has, the proper word is exhibits state-independent contextuality. So in this word, what does it mean to exhibit state-independent contextuality? It means that we cannot have a function which assigns to all observables one of its eigenvalues, such that all relations which we would like to have will be will still hold. So it is called probably consistent value assignment, or yeah, okay, something like this. And in this paper, the authors also consider an action of a group G on the set O. in such a way that this action descends to E. So that means that G fixes ZD. And then we define a kind of strange function, and strange because this particular formula was actual motivation and question for the whole project, a function phi by GTA is equal to phi GA times TGA for all G in G. Now we can treat phi as an element of C1 of G with values in C1 of E in ZD. So in particular, phi is an element of a double complex C star E, here I should have G, C star E varies on ZD of by degree 1, 1. However, beta also belongs to this double complex and has by degree 0, 2. So we can actually ask whether these two functions are anyhow connected, and the answer is yes. So the two formulas which we have is that firstly, the horizontal differential of phi in this double complex is equal to 0, and the vertical differential of phi is equal to the horizontal differential of beta. Now, phi can also be used to detect contextuality, but that's not so easy as it was in the case of beta. So instead of discussing this, I will just state that phi can be used to detect contextuality. So the main message of this second part of motivation is that cohomology can be used to detect contextuality, and that's no surprise, but we would like also to see how group action and group cohomology can be used to detect contextuality. So now let's discuss a little bit cohomology for contextuality. Or maybe I should say also G contextuality. And this will be first approach. So let's start with cofibre sequence of simplicial sets. Z goes to X bar. And then we have the following diagram. So deterministic distributions on X bar and A to deterministic distributions on X and A goes to deterministic distributions on Z and A. Here, these things are isomorphic to first cohomology of X bar with values in A, first cohomology of X with values in A, first cohomology of Z with values in A. So what we see in the bottom row is really a long exact sequence in cohomology. And the next step in this long exact sequence is, I will write it like this, the map zeta, which goes to second cohomology group of X bar A. And here zeta is just the connected homomorphism in the long exact sequence for cohomology. Now, if we take Z to be equal to NA, then we can define the class gamma, the cochain gamma, as a connecting homomorphism on the identity. And here I'm sweeping a little bit of things under the carpet because I can identify the first cohomology of NA with values in A. So this thing is actually can be identified with group homomorphisms from A to A if Z is equal to NA. So identity in this sense, so this is identity from A to A. And we get that the inclusion I from NA to X has a section if and only if the class of gamma is equal to 0. And if this class is not equal to 0, then all simplicial distributions P from X to dr and A are contextual, here relative to NA, are contextual. So far, this is still work of Cihan, Aziz, and Selman in simplicial quantum contextuality. The only difference in this proposition is that in their original work, they considered A to be equal to ZD. Here we have all abelian groups A. So now let's turn to the equivariant distributions. So firstly, we record the following lemma. So we have the following, for this lemma, we have the following diagram. So we have Y x bar, g bar, and here we have y Borel construction on y, x bar g, and here we have x bar Borel construction. Okay. This is equal. Now, all columns here are cofibre sequences. Yes, and let's call some names. And the lemma states that the inclusion, here y and x are G simplicial sets. The inclusion I going from y to x has a G equivariant section. Sorry. If and only if J from y to x border construction on x has a section. If and only if J going from y to y Borel construction. Here I have IG, X, G has a section. So coming back to this diagram, this lemma is saying that if we have a section here, G equivariant, then we have a section here, and we have a section also going here.
This
Now,
sounds a bit, sorry, this sounds a bit duplicate, right? The second and the third seems to be the same thing. Huh? They seem to be the same map.
In what I have written or what we have in the paper?
I think I think you meant that the middle map, which is called I sub G.
This should be sorry. This should be I sub G, and I have J here. Yeah.
Yeah, okay. The middle thing goes from Y Borel to X Borel.
Yeah, sorry.
Right?
Okay.
Yes, I mean this is. I think that's the third map on the right. Yeah.
So we have, if we have a section here, we have a section here, and also we have a section here. Very good.
Yeah. That's what you're.
Okay, thank you. So now we would like to have similar idea to detect G-equivalent contextuality. So now we use the middle cofibre sequence. So the middle cofibre sequence is the following one. We start with NA goes to X /G goes to X /G. And here this is G equivariant inclusion. So now, once again, using the long exact sequence in cohomology, we have the connecting homomorphism from, so this will be zeta from H1 and A going to H2 X Borel construction bar to A, and then we define gamma G to be once again the connecting homomorphism on the identity. And by the definition of this cochain, if we denote in our diagram, if we denote this map over here by iota bar, then we have that iota bar star of gamma G is just equal to gamma. And this is the class which we will use for detecting G-equivariant contextuality. So the proposition is that the inclusion J from NA to the Borel construction X has a section if and only if the class of gamma G is equal to 0. Moreover, if the class of gamma G is not equal to 0, then every simplicial distribution P from X from the Borel construction on X to the RNA relative to NA is contextual, and from this we can derive by the previous discussion that that means that if this class gamma G is not equal to 0, then every G distribution P from X to DRNA is G contextual. Okay, so this is one of the connections which we have. So by detecting and by studying cohomology of the Borel construction, we can see which distributions, or rather whether we have any G-equivalently contextual distributions or not. But we would like to further connect it to the topological parity paper. And for this, we need a double complex. So for a simplicial set, for a G-simplicial set X, we define a bisimplicial set as a G of X will be EG here PQ, EGP times over G with XQ. And well, it's easy to see that the diagonal of this simplicial set, bisimplicial set, is the Borel construction on X. And there are two chain complexes associated to this bisimplicial set. So the first one is the chain complex of the diagonal, well, of bisimplicial abelian group, free abelian group on SGX. The second one is the total complex of the chain complex, of the double complex associated to the free bisimplicial abelian group, yes. And by the Eilenberg-Zilber theorem, these two chain complexes are chain homotopy equivalent.
Igor, sorry for interrupting. So I just want to remind you the time.
Yes, I know. So actually, I will just finish the first approach. I will show the yes, how we see these classes in the double complex, and I will just mention how the second approach goes without going into details.
Oh, okay. Yeah, I just wanted to remind you. For me, it's fine, but maybe some people are going to leave for some other thing. Okay.
Yeah, I know. It's 15 minutes only, right? Because it's 1.5 hours. Okay, very good. Okay. So, well, okay. There are specific maps. Oh, sorry, the tablet disconnected again. Okay, so let me just write that there are two maps connecting this. I mean, the Eilenberg-Zilber theorem is saying that these two chain complexes are chain homotopy equivalent, and there are specific maps, explicit maps giving this equivalence. So first is called as Alexander-Whitney map, and it goes from this one to this one, and the second one is called Eilenberg-Zilber map, and it goes from bottom to the top. So using the Eilenberg-Zilber theorem, we can get the following result, that under the Eilenberg-Zilber map, so this is denoted by nabla, the cocycle, actually here this should be a dual of the Eilenberg-Zilber map, the cocycle gamma G in C star X G bar A is represented by the triple 0, 0 gamma in the total complex. Okay, and here I just wanted to mention that this is a little bit more complicated way of capturing the following difference, that contextual implies G contextual, but opposite doesn't have to be true. And how do we see this? Well, so if we are in the total complex, here leaves the class gamma, here leaves 0, and here leaves 0 in this by degrees. Now, so let's think about non-contextual things. If something is G non-contextual, then the class of gamma G is equal to 0. But that means that this whole cocycle in the total complex is a coboundary. So in particular, there exists two cochains, of degree 1, 0, and 0, 1, such that they will hit gamma, and under horizontal and vertical differentials over here, there will be 0. But on the other hand, if something is G non-contextual, that only means, oh, maybe I will write it in other color. Sorry, so we just want non-contextual. So we only know then that the class of gamma is equal to 0. So in this case, there is a class here which hits gamma, but we don't know, and we cannot be sure that the horizontal differential of this class will be equal to 0. So this is how we capture in this total complex, in this double complex picture, the difference between contextuality and G-contextuality. And in this blue case, so maybe I will actually continue to write it in blue, we capture this difference if gamma is equal to 0, then there exists, well, R going from yes, just a moment. In this case, R will go from X bar to A, X bar 1 to A, such that dr is equal to gamma. And then we capture the difference between G-contextuality and non-contextuality by class phi, which will be defined then as the horizontal differential of this class R. So R in this case lives here. Okay, so this is our first cohomological approach to contextuality. So let me quickly mention the second approach, which will be partial groups. So here, the idea is as follows, that if we use the notion of a partial group from a paper of Broto and Gonzalez, so that partial group is a simplicial set such that its spine map is injective. And we think about extensions of partial groups as fiber bundles. Well, we have a couple of things here. Fiber bundles are usually, by work of Peter May, I suppose, not only, are described by twisting functions. But in case of partial groups, these twisting functions are described just by degrees 0 and degrees 1 and 2, and all other degrees are defined. So we can think about this extension of partial groups as just a fiber bundle, and we can consider a pseudo section. So map, nearly simplicial map. So this is eta. Here is a map which preserves all simplicial structure except T0. And then we can define the class beta from M2 to A as beta of x and y, eta x, eta y, eta x, y inverse. So this is exactly the same formula which we have for the extension of groups. And what we will get is once again that if the class of B is non-equal to 0, then simplicial distributions on E to an A relative to an A are contextual. But we can also endow this extension with a group action. So the only assumption here is that this group action actually on E has to fix A. And then we can define also another class phi, which go from G times M1 to A, which is, and it is defined as phi of Gm is equal to G eta G inverse M times eta M inverse. Now, if we have such an extension, what we get also is an extension NA goes to E, the Borel construction on E goes to a Borel construction on M. And here we can define pseudo section eta G coming from eta. And then we can also define class the cochain beta G. Once again, by the Eilenberg-Silber map, we get that beta G is represented in the double complex in the total complex by the triple 0, phi, and beta. Okay, so yes, so I should say that the bottom point of all of this discussion is that there is a comparison of these two approaches. Which well goes simply by the following diagram. Here we have a cofibre and sequence. Here we will have fiber sequence. Yes, and using this comparison diagram, we also get as a bottom point that in the non-equivariant case, we get that here I should say that I from NA to E has a section. Gamma is equal to 0 in H squared E bar E, and beta, the class of beta is equal to 0 in the second cohomology of MA, of M with coefficients in A. And also if we decorate these classes with G, we have that the following are equivalent. This inclusion has a G equivalent section. And this is equivalent to I from NA to EG has a section. Which is equivalent to BG being equal to 0, which is equivalent to gamma G being equal to 0. Okay, and I think I should stop here, so nearly on time.
Okay, thank you, Igor. Any questions for Igor? Maybe I should comment on the topological parity part that you mentioned. So just as a comment, so that part is described using the partial group approach. So that was kind of our starting point, and then we work towards the cofibration point of view, which is easier.
Yes. So I didn't get actually to partial group extensions, but this was stuff which we spent most of the time actually. Yeah.
So the other thing, I mean, so the goal here was to describe this phi class that Igor mentioned in the topological parity paper. We were trying to describe it using some spectral sequences because lives in a double complex. And the original description is a bit weird, and it's not really a natural definition what a topologist would do. But then, as we were trying to figure that out, we have observed that the main class was not the phi, but the beta G or the gamma G class. So we started to concentrate on that class, and it turned out that class actually was detecting equivariant contextuality, and that was something unexpected and surprising in this project. So.
Igor, I said this before, but I should also mention that these are probably better. You can put this into the context of extensions of categories. Partial group approach also probably fits into that. And for extensions of categories, there's the Lindenhoff-Serre spectral sequence, which is pretty much obtained by this double complex that you mentioned. You get it as hypercohomological spectral sequence. And differentials there also coincides with your differentials, I think. So I don't know if computational, though, either approach like will give advantage. Like what you try to compute, I don't know exactly, but there's definitely a more general context of extensions of categories. For example, the Borel constructions can be taught as Grothendieck construction, realization of the Grothendieck construction of a G category. So there's a category there too, like the whole Borel construction is the realization of the category obtained as a Grothendieck construction. In G category, there is a functor from G to the cut, where the unique object goes to that category. So the Borel construction naturally comes as the realization of the Grothendieck construction of that functor.
Oh, okay.
So that's also a category. So the approach with the Borel construction also realization of a category. So I think you should look into this extension of categories, and the Lindenhoff-Serre spectral sequence has a similar structure, I think, to what you're doing here.
Yes, thank you. So, I might be wrong here, but
how that can help you, of course, I don't know.
So I might be wrong here. So if I'm wrong, Cihan, please correct me. But the idea here is also that we would like to stay more closer to the ground, because this whole project is done with a view towards actual computation, which is called measurement-based quantum computation. So this is why I mean, of course, well, this is one of the reasons why we stayed closer to the ground. But yes, maybe extension of categories is the next direction we should take a look at, especially since these partial groups appear here.
Yes, so maybe the categorical approach might help too, just to put it into a nicer framework. Yeah, we haven't thought about it. But yes, as Igor said, so what we want to essentially compute here was, we wanted to detect equivariant contextuality using one of those classes, which is the class phi. So just computing phi on a simple example would be good. And we were mainly trying to come up with the simplest example, essentially, which happened to exist in the cofibration picture rather than the fibration picture, because in the fibration picture, total spaces tend to be quite large, because you have this fiber, which is a nerve of a group, so it's something quite large. But for cofibrations, we happen to observe that the very small example, that's essentially the first example that Igor mentioned at the beginning of the talk, this torus example with this Z2 action. So we were mostly focused on explicitly computing these classes on those examples and see what we get. And then at the end, we are planning to write this follow-up paper, which is going to be on computing using simplicial distributions. So this is another idea that essentially due to Robert, who came up with this cohomological framework for measurement-based quantum computation that's based on the topological parity paper. So we want to do a counterpart to that using simplicial distributions and a new phi class, and eventually understand what equivariant contextuality means in that context, because that's the new part physically. I don't know. So that notion is new. So we want to understand. So that's kind of why we are trying to stay concrete. But probably we should also think about extensions of categories. I think that could fit it well as well. Yeah. Okay, any other questions? Okay, so if not, let's take Igor. Thank you, Igor.
Thank you.